Okay, so what we're doing today, with the second part of Unit 6, Unit 6.1, second part. What we're doing in this video, I've split Unit 6.1 into two parts just because it's kind of long. This part 2, we're going to go over unit vectors. Unit vectors. We're going to go over vector notation. We're going to go over resolving the vectors. We're going to go over example 5 and example 6. And then the last one that we're going to do in this video is example 7, and that is a bearing problem. Those come back again in this unit. So those of you that kind of had a hard time with it a couple sections ago, last chapter, we're going to go over that again, but hopefully we'll, this time around, we'll get a little bit better at what it is that we're trying to get you to learn. Okay, so here we go. I'm going to go to the next slide, and we're going to go over unit vectors. Okay, so what's the deal about unit vectors? If you have a vector u with the length of 1, so is this going to go over unit vectors? If you're given a vector u, again we're going to highlight it in your notes. It's highlighted u. If it has the length of 1, which means it has the magnitude of 1, that's called a unit vector. It's just one unit. Okay. One of the things to find a unit vector, what it boils down to is you can take the component of any vector, the component form of a vector, and remember, I'll talk about that, hold on a second, vector, and divide it by the magnitude of that vector. Okay, so really to find a unit vector, I'm going to call that u. What that is, I'm going to you have a component form, and you're going to divide it by, like you have component form of AB, that's your vector, and you're going to divide it by the magnitude of that vector. The magnitude, again, is denoted by like those absolute value symbols. In your notes, they use this, the component form of V, divided by the magnitude of V. Okay? Not too bad, but let's do an example of what they have in your notes. All right. I guess in your notes, actually, I think there's another way of writing unit vectors. Is you can write it as, I guess I need a pen to write on it. It can be written as 1 divided by the absolute value of the vector times the component form of the vector. Your book says unit vectors provide a way to represent the direction of any non-zero vector. Any vector in the direction of v, or the opposite direction is a scalar multiple of its unit vector u. Okay, blah, 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 yada, yada, yada. Well, you want to know how to find this. The example 4, it says, find a unit vector in the direction of v has a component for -3 and 2, and verify that it has the length of 1. So they give you this vector. And they give it to you in its component form. And I know it's component form, guys. Let me remind you, when you see this like arrow kind of looking things, that's to denote that's its component form. There's another way of writing those. It's something you might see in linear combination, but we'll talk about that in just a second. So you're given a vector, and you want to write it as a unit vector. You give it to you in its component form. The first thing I want to be able to do is find the magnitude of this vector. I remind you the magnitude. We're going to use that lovely distance formula. But one of the things too, if it's already in component form, I can realize that the component or the magnitude of this is going to be right magnitude, Miss Andrus, is your a, the square root of your a squared plus your b squared. I guess I was saying b, but I really should have written 2. Okay. So then this will be the square root of 9 plus 4 equals the square root of 13. Alright, so the magnitude of this vector is the square root of 13. Now to write this in as a unit vector, I can write this. I'm going to use this equation right here. This equation I'm going to use. I'm going to write as 1 over the magnitude of v, which happens to be the magnitude of your vector, is the square root of 13. 1 over the square root of 13, and then I'm going to multiply it times the v, which is this piece right here, the component form of your vector. Multiply it by -3, 2. Okay, and I showed you how to do this in the first part of your the notes, 6.1, part 1, about doing this. You're taking this, okay, this right here, this is a scalar. What that means is just a number. I'm going to take that number and I'm going to multiply it times the component form of a vector. It's almost kind of like I'm going to distribute it. So what I'm going to do, like I said, we talked about doing that in the first part of 6.1. I'm going to multiply 1 over the square root of 13 times -3, and then I'm going to multiply 1 over the square root of 13 and multiply times 2. To write this in your component form, the unit vector in component form, well, we're multiplying fractions, I remind you, 1 over the square root of 13, I'm going to multiply, this is a fraction, I'm going to multiply fractions, you multiply the numerator, so 1 times -3 is -3. You multiply the denominators, well, the denominator of -3 is 1, so the square root of 13 times 1 is the square root of 13. You're going to do the same thing here on the second, the b component. 1 over the square root of 13. Oh, I wrote this wrong. This is the square root of 13, not 3. Going to multiply 1 over the square root of 13 times 2 is going to be 2 over the square root of 13. Okay, this is the unit vector. This is the vector v in unit form. Just the same, just a different form. Same vector, different form. Now, what it wants us to do is to verify that this magnitude, like this vector, which it's written like this, it wants to make sure that the magnitude or the length is 1. So again, what I'm going to do is find the magnitude of this vector, which means I'm going to use that equation, find this. I'm going to square my a term and add it to the square of my second term. Okay, actually I'm going to take the square root of my a component squared plus my b component squared. Okay, on a side note, this means -3 times the square root of 13 times -3 square root of 13 plus 2 over the square root of 13 times 2 over the square root of 13. Alright, when you see this, hope you'll realize -3 times, I'm going to multiply fractions here. Multiply -3 times -3 is 9. 9 over square root of 13 times the square root of 13 is 13. Plus, multiply the numerators and the second fractions. 2 times 2 is 4. Square root of 13 times the square root of 13 is 13. Okay, I'm adding fractions. They already have a common denominator, which is 13. I'm going to add my numerators. 9 plus 4 is 13. Hopefully you all realize the square root of 13 divided by 13 is 1. The square root of 1 is, this becomes the square root of 1, which happens to be 1. Therefore, we have verified that this unit vector, it's in component form. It's vector v written in component form. It has the magnitude of 1. Okay, All right, now what we're going to do is we're going to talk about, there's a little box on there in your notes, and it gives you this notation that if you're given a vector v, I guess I have to have a pen, sorry, vector v written in component form has the components of a, b. Any of these vector can be written in what they call as a linear combination. It can be written also as a times I, the cursive I, plus b, the cursive j. If you're in physics, AP physics, pre-AP physics, you guys might have already learned this. This is called the linear combination. And really what where that comes from is if I have, if you're on the x and y axis, and you have a vector v. Again, vectors show something, an object that has direction and magnitude and length. This is vector v. It can be written as this way. It also, what I can do with this, it could have the scalar, your a and your b's are just scalars, or constants, or numbers, can be written in that form, but then the I and the j tell you its horizontal and vertical components. Your I is your horizontal component, like this right here. Really what I'm doing is I can kind of split this vector into a horizontal component, which we're going to call AI, and its vertical component, which is called BJ. Right? It's just another way of representing the same vector, but split it with showing that in its your horizontal component and your vertical component. All right. Then the next one we have is I'm going to do in the next slide, slide 4, is resolving the vector, which kind of nice because, well, it's just another way of writing a vector. Okay, we're going to go over example 5, but one of the things is, in the previous slide we talked about one way to write an angle, or vector, is in linear combination. Now what we're going to talk about is if you have a vector that actually has a direction angle. And you might recall that we did application problems in section 4.8, or you might have done section 4.8, that direction is measured in different ways, especially in navigation. And one of the big things about navigation is your navigation is from due north, or the bearing is from due north. But another way, very kind of convenient way, to specify the direction of a vector is to state its directional angle, and the angle theta that the vector makes, or vector v makes, with the x-axis. Again, I said this lots and lots of times, but lots of students make the same mistake. Theta is the angle that you're making with the x-axis, and the same thing is going to hold true here. If I have an x-axis and a y-axis, and we have a vector, I'm going to call it vector v, and it represents something that has direction and magnitude. But if it has a direction, if it has an angle with the x-axis, that theta is the angle this vector makes with the x-axis. Another way of splitting out this vector v, is to have, we're going to call it resolving the vector, but we're going to have a horizontal component and a vertical component. I have a horizontal component right here, and this is how I can find this. Just like when you were doing trig, it's going to be my vector v, and the magnitude of vector v, times the cosine of theta. And the reason I'm doing cosine of theta on this horizontal component, if you remember, the horizontal component, or this is your cosine, is your x value. Then if I wanted to figure out the vertical component, and this is dealing with vectors that have, again, have an angle, that have an angle theta with the x-axis. The vertical component I can write as figure it out or find it by the multiplying the absolute value of vector v, or the magnitude vector v, times sine. Ooh, Miss Andrus, can't really see that. Times sine of theta. Okay. This is called resolving the vector. And again, if vector v has the direction of angle theta, the components v can be computed using the formula. So I'm going to write this formula down. V, and in your notes they bold it. Vector v can be found or split in components as I'm writing this in component form. Could be the component written as the absolute value or the magnitude of vector v times cosine theta. It's kind of like your x-coordinate. And your b-coordinate would be the absolute value of magnitude of v times sine of theta. So you had another way of finding, writing any components of vector v. If you have the unit vector, this is on a side note, I don't know if this is in your notes, to find the unit vector, one way could be cosine of theta. This is only if it's the unit vector, cosine of theta times sine of theta. Okay, so I'm going to do example 5. In example 5, it asks you to find the components of vector v with a direction angle of 115 degrees and a magnitude of 6. I'm going to kind of scroll up a little bit here. Maybe it won't let me. Alrighty, well, I guess I'll write it in this space. Okay, so I'm going to draw my x and y, the picture. I don't know if they provide the picture in your notes, but I have the x-axis, the y-axis. I'm going to do my, tells me, this is example 5. It tells me that my vector v has the magnitude of 6. That means the absolute value of v is 6. And then it's and it makes the angle with the x-axis, theta, is 115 degrees. Okay, so they want us to write this in component form. And again, I'm going to use this equation right here. This one, again, this is only for unit vectors. This is not a unit vector, what they gave us. The reason in problem example 5, it's not a unit vector is because the magnitude is something other than 1. So I actually have to use this equation when I'm doing example 5. I'm using this function right here. And guys, this is about as easy as I'm going to plug it into this formula. V, to find it in component form, it would be the absolute value. Write this in component form. It would be the absolute value of v, which is 6, times the cosine, 115 degrees. Its b component would be absolute value v, which is 6, it gave us, times sine over 115 degrees. Okay, that's in component form. If you gave that to me as a test, I probably wouldn't give you credit, mostly because I would want to find what the cosine of 115 degrees is, and I definitely would want you to multiply 6 times it. But this 6 times cosine of 115, that should be about negative 2.54. And the 6 times sine of 115 degrees is about 5.44. Okay, this is in component form. Kind of makes sense. Really, if you kind of can relate this form into an x-coordinate and y-coordinate on a coordinate plane, again, we're trying to make one-dimensional things into two-dimensionals. My x is going to be, my x-coordinate is going to be negative. It's not because I'm in the second quadrant, and my y value is going to be positive 4.44. Okay, so that's example 5. I'm not sure what example 6 is. Oh, example 6. I'm going to start a new slide for these because they're kind of long. And if you don't have a calculator, you're going to want to get a calculator. I'm not sure how to import my TI Nspire in this demonstration. I guess that's for experts only. But anyway. Alright, example 6. They want us to find the magnitude and direction angle of each vector. So in letter A, they give you the vector u. And again, your book highlights it, and I think your notes try to bold it. They give you vector u in component form. And they want you to find theta, the direction angle, and then the magnitude. So I'm going to, on the side note here, I have my x-axis and my y-axis. They have this vector u, and they give me the magnitude of 3, 2. And I kind of know that it's going to be in this first quadrant because my A value is positive, my B value is positive. They want to find this. Theta. Your book actually is alpha, I think, the equation, but really don't want to confuse you because they want to find the angle it makes with the x-axis. Because that's what theta is, that's your directional angle. Alright, the first thing I'm going to do is the magnitude because I think that's probably the easiest thing to find. I don't know. You're going to be very happy and well versed in finding magnitudes of vectors. It's in component form. I don't need to use the distance formula because I don't have a starting part. I mean, like, it's already in component form. I don't have to. They don't give me the starting point and the ending point. They've already put it in component form. So my magnitude is going to be 9 plus 4, which happens to be 13. They love the square root of 13 for some reason. So the magnitude of this unit, the length of this vector, happens to be the square root of 13. Whatever. Okay, now what it wants us to do is to find theta. Well, what I do have, I have really the length of this. I have this. I guess kind of like I have the hypotenuse. I have this value. Okay, and they've already told me that this value is the square root of 13. Okay, they want to find this theta. Okay, so really they want to find theta, which is the directional angle that it makes with the x-axis. And there's a couple ways I can do this. One of the ways, you could do trig, so I'm actually going to find, we know that this length right here would be the square root of 13 times cosine of theta. Hopefully that kind of makes sense, because it's your radius times this length, or that's what this length is your radius times cosine of that angle, because that's that horizontal distance. Don't know what theta is, but I do know this length. I know they already told me that this is 3. This, if I wrote over here, square root of 13, this is 3, and this is 2. I can set this 3 equals the square root of 13 times cosine of theta. So again, we're trying to find what theta is. So I can divide by the square root of 13. Move up a little bit. So just to keep it neat, I have this. 3 divided by the square root of 13 equals cosine theta. I'm looking for theta, so I gotta find cosine of what angle equals 3 divided by the square root of 13. This is when a good application of your inverse function is. Oops. Three divided by the square root of 13. That's what's going to give us theta. Okay, that's a great application of how to find an angle given the hypotenuse and a side, or inverse. Inverse angles are good for finding the angles. That's what the whole purpose of that is. And if you found that your calculator made sure that you put it in degree mode, your angle would be about 33.69 degrees. Alright, so that's letter A. Let's see if we can't do letter B. Letter B. Oh, snap. Oh, okay. That's weird. I guess I'm going to start a new slide for this one. Okay. So now we're going to do, I'm going to do example 6b. This is asking again to find the magnitude given vector v. Given a vector represented by v, I guess. Semantics, not my best thing. Given its component form is -2, -5. Okay. On a side note, this vector v, I'm going to erase this, put a different color. This vector v is going to be in the third quadrant because from here to here, right, this is -2, and from here to here is -5. It has to be in quadrant 3. So the angle that it's making, that this vector is making with the x-axis, that's what I need to find. And I'm going to call that theta. I think your book calls it something else, or beta. Your notes might call it beta. But I need to find what that vector is making with the x-axis. That's how this works. But one of the things that I'm going to do is, when we did it a couple sections ago, we did a reference angle, and we kind of broke it down into parts. Still can do that. I have a vector v. This length is -2, or just 2. And from here to here is 5. And I can call this theta, because that's the angle this vector makes with the x-axis. Well, I guess that's kind of why your book calls this beta. Makes a little bit more sense. So that's beta. So the first thing I want to do is I want to find the magnitude, the length of this vector. And the magnitude is going to be -2 squared, square root of -2 squared plus -5 squared, which is going to be the square root of 4 plus 25. Oh my god, it's not 13. It is the square root of 29. Can't believe that's actually something other than square root of 13. Okay, now the thing is though, what I want to do is, I know this distance, like this right here, is what we did before, is we set this length, -2, equal to the magnitude of v, square root of 29, times cosine of theta. And this is kind of where it makes sense to have different variables, different symbols calling different angles, because theta, again, is the angle that your vector is making with the x-axis. Eventually we've got to find the big total direction that makes, we're going to have to find beta, but I want to find this small angle first. Again, let's do this. I have, going to divide both sides by the square root of 29, so I have -2 divided by square root of 29 equals cosine theta. Again, I'm trying to find theta, so I'm going to use the inverse. Find inverse of -2 divided by square root of 29. That's what's going to give me theta. Which, that angle, that small little angle, is going to be, I don't know, I'm going to pause this and find what that angle is. Okay, so I'm going to make sure my calculator's on degrees. I'm going to do inverse cosine of -2 divided by the square root of 29. Okay, this is going to be 80 degrees. Okay, but that doesn't make any sense. hold on a second. Alright, so just a minute ago, I said this doesn't make any sense to me. And one reason this doesn't make any sense is because, is that why did I get 118 degrees, 111.80 degrees? It makes any, like, I'm having a hard time getting my brain around it. One reason it's not making a whole lot of sense is because when I drew my angle up a minute ago, I, up here, I'll keep sliding these word crap, is that I was in the third quadrant, and 118 degrees is not, 111 degrees is not in the third quadrant, it's like in the second quadrant. And so, really I'm right here. 118 is in the second quadrant. When I drew it, it was supposed to be in the third quadrant. So really what I'm supposed to do with this is I need to take 360, subtract it from 360 degrees, and that's going to actually give me the angle that it makes with theta, and with the x-axis. And it makes a whole lot more sense, because if I do that, I'm going to get 248.2, and that's something that's going to be in between 270 and, like, my angle has to be between less than 270 but greater than 180, and so that's how we get this angle. It's kind of a strange problem, but needless to say, this is a strange class. But how you find the angle that it makes, the directional angle. Okay, I am going to do the last problem, which is the application of vectors. Okay, application of vectors. The velocity of a moving object is a vector because velocity has both magnitude and direction. So, the magnitude of velocity is speed. Really what that means in English, if I'm given speed, like in miles per hour, that's the magnitude of your vector. Okay. So, in example 7, it says the DC jet airplane is flying at the bearing of 65 degrees at 500 miles per hour. Well, first thing I'm going to do here is I have my airplane, and it's flying in a direction bearing 65. Again, bearing is from due north. This is your north, and it's saying that it has the bearing of 65 degrees. Okay, but when we are doing this, you have to remember this is theta. When you use that formula, theta is the angle your vector makes with the x-axis. So really I care about this angle, this FYI, and that angle is 25 degrees. Okay, it says that the plane is flying with a speed of 500 miles per hour. So what they're really giving us is that's our magnitude of this vector, because it flies at 500 miles per hour. And then it says find the components form of the velocity of the airplane, and we call the bearing as the angles from travels due north, measure clockwise. All right, it gives you this problem, and it wants it in component form, so it wants your vector in this form. Okay, what's in component form? If you're given a velocity with an angle or with the direction, I need to write it to find it in component form. This is the equation I'm going to use. Okay, again, theta is the angle the vector makes with the x-axis. They gave me what the magnitude of this vector was. It was 500 times cosine of 25. And my b component is going to be 500 times sine of 25. Okay, this is kind of easy because my bearing, it's the equation I'm going to use is 25 degrees. It was an easier problem than example 6b. It was a little kind of weird. But anyway, I can put this in the calculator into degrees mode, and I'm going to have 453, 15, and miles, and then 211 miles. Okay, now let me kind of talk about really what this means. Okay. What this answer means is that my plane is going 453.15 miles per hour in the direction, because this is your x coordinate, so I'm going eastward, then I'm going 211 miles per hour northward. Okay, when they ask you to do this in component form, that's really what they're doing. They want to know how if in the eastward, if I just was going straight east, I was going 453 miles per hour. If I'm just going due north, I'd be going 211 miles per hour. But I'm not. I'm actually going northeast, but this is how you split it up in component form. Okay, have a go at your homework. I'm going to try doing section 6.2. Okay, I don't know if I was explaining this. I think I probably was not recording this when I was explaining this. This vector in component form, 453.15, that's telling you you're going 453.15 miles per hour eastward. This is eastward direction. And then you're going 211.31 miles per hour in the northward direction. That's what they want you to do, is if they want to split it in component form, or write it in component form. Okay, have a go at your homework. Doing this. Hold on. I have it in component form. Uh-oh.